This is Matt Rosen from the MGH Martino Center. I'm a founder of these four companies. I'm on the Scientific Advisory Board of AVQMR, and I receive sponsored research from GE Healthcare. It's so exciting the way low-field MRI has captured the imagination of the ISMRM. Steve Schiff, 2 years ago in his plenary, talked about low-cost MRI potentially revolutionizing global healthcare, and that low-field hardware would be a part of this. And just last year, Andy Webb in his plenary taught us to disrupt the way that data is gathered using low-field MRI, and most importantly, to embrace the impossible. With that as a background, I'm very happy to talk today about Millitesla MRI in my laboratory. We get into a lot of things in my group, and those of you who met me in the 90s probably think of me as a hyperpolarized gas guy. But for the past 20 years, first in Ron Walsworth's lab at Harvard, and then over in my group at the Martino Center, we've been involved in the Millitesla regime. Everything else on this list are either enabling technologies or applications that benefit from operation at low field. And I know it's a big list, but I want to give you guys all a flavor of this work. The problem is very simple. What kind of MRI can you do here if all you have are multi-Tesla instruments? And the reality is you can't. In the presence of undisclosed shrapnel, these machines could be potentially deadly. This point was driven home to me in 2010 when I got a grant from the DoD to see if there was a way we could leverage work we were doing in my laboratory at 6.5 millitesla and now applying it towards neuroimaging. 16 years ago, I was talking about the design and construction of this 6.5 millitesla scanner built by me and my student Leo Tsai. We were interested in doing hyperpolarized helium-3 lung imaging, and in 2008 we published some of these results. The following year we packed up the scanner and moved it to my lab. That's our student Stephen DeVince supervising. And then in 2010, Popular Science gave us the moniker the do-it-yourself MRI. So I want to talk today about how we solve a hard problem, which is enabling MRI at ultra-low field strengths. And I'll talk about a combination of physics and compute strategies. The physics strategies are really about maximizing the SNR in your preamp. And the compute strategies are, once you've sampled that data, how can you apply techniques to it to reduce noise or get more information, or what the kids today call it, fixing it in post. SSFP has turned out to be a very valuable workhorse for us because signal averaging is a real painful reality at 6.5 millitesla. SSFP has a very high data rate and is very efficient. The cartoon of how it operates looks like this. You coherently drive the magnetization back and forth, and you get to a steady state value that can actually be quite large. This sequence is fully compliant with the three rules that we've sort of devised over the years about how to do low field MRI, and they are: make the most of what you have. If you have very small Boltzmann polarization, you should sample all of it, so large tip angles are typically quite nice. You shouldn't waste anything, so don't crush magnetization, but rewinding it and refocusing it is good. And don't delay. Remember, we need a high data rate because we have to do signal averaging. Hermann Carr recognized this in 1958 when he first wrote down the SSFP equation. Of course, he wasn't doing imaging, he was doing spectroscopy, but he had a low field magnet and he had long T1s, and he didn't want to wait either. So applying SSFP at 6.5 millitesla gives you some pretty amazing results. These are brain images we published in 2015, 2.5 millimeter in plane, acquired in 6 minutes. And if you compare that to images we acquired in the same scanner back in 2005 with the wrong sequence, a 2D gradient echo in this case, you can see why you really want to think about your choice of sequence if you need to do signal averaging and high quality imaging at low field. Just a few words about our coils. Most things are harder at low field, but building coils is much easier at low field. And the way we do this is you take your coil, you wind it on your former, you plug it into your network analyzer, and you click your tune and match capacitor decade boxes until it's tuned and matched. And then you solder those values right in. It's the easiest thing in the world, and my colleagues who work at high field with high frequency coils are very jealous of us. So what I've plotted here is the signal equation for SSFP as a function of frequency offset. And SSFP, of course, requires very high absolute B0 homogeneity. Something like better than 10 Hertz over the whole field of view, in this case, if you don't want banding. That's 36 parts per million at 6.5 millitesla, which is actually quite a very easy engineering burden, but it's 100 parts per billion at 3 Tesla, which is essentially impossible because of magnetic susceptibility artifact. So if you look at the images on the right at 3 Tesla, of course we see banding, and in the same subject at 6.5 millitesla, there's no banding. The reason this matters is quite interesting, actually. This is a clinical TBI subject who had open skull TBI followed by surgical resection and a cranioplasty with placement of titanium mesh. If you look at the images at the top, especially in the highlighted regions, you can see there's large susceptibility artifacts in the region of the titanium mesh. At the images on the lower part, acquired at 6.5 millitesla, you can see much clearer outlines of the surgical resection. This matters because imagine that this patient had a post-surgical bleed in the area of the surgical resection. You might not see it at 3T, but you could see it at low field. So SSFP at low field is maximally efficient, and that's of course because the signal equation goes like T2 over T1, and at low field, T2 gets longer and T1 gets shorter, and that ratio turns out to be around unity. That means we operate where this red curve is, around 90-degree tip angles. The problem with that, though, of course, is that our images are essentially proton density. And that's really a shame because we have all of this interesting T1 dispersion at low field that is untapped by this sequence. So thus far, I've talked about how to do fast acquisitions where you make good images by averaging. But you can use fingerprinting to maintain a high data rate, but instead don't operate in a steady state and don't signal average, but continuously vary your acquisition parameters, typically your tip angle and your TR, and acquire all of those images. This is what fingerprinting looks like at 6.5 millitesla. This is a 3D sequence. It's a very, very short schedule, a 20-point optimized schedule. This comes out of Ori Cohen's pioneering algorithm for schedule optimization. And you can see the images coming in, and there's banding, and the banding moves around depending on the TR and the tip angle, and we save all of those images. Reconstructing, of course, you can get the proton density images back, which is basically what we would have got with SSFP. But then, when you fully reconstruct it, you get the T1, the T2, the off-resonance map, and the B1 map, all in a reasonably short scan of 23 minutes with only 4 averages. You can do the same thing in vivo, and the beautiful part about this is now in a very short scan, 16 minutes for us, you can now have a way to access this extremely interesting region where there's a lot of T1 dispersion. So we continue to evolve our hardware. This is a quadrature coil that Neha Kunju built, taking a page from David Holt's work, and it gives us a factor of root 2 in SNR, for which we're very grateful because that's a factor of 2 in acquisition time. But at some point in time, we're out of ideas. Our sequences are maximally efficient. We're at the Johnson noise limit. We have no other place to go. So what do we do? Well, the joke in my lab is that, well, we can't improve the signal, can we just reduce the noise? And so about 2 years ago, my postdoc Boju took this very seriously when he wrote down his pioneering deep learning for image reconstruction approach called AUTOMAP, Automated Transform by Manifold Approximation. And it's a data-driven approach that learns to invert an arbitrary encoding based on knowledge of the forward model, but most importantly for this work, it operates on a learned joint sparse manifold, which allows us to improve the SNR and the accuracy of the reconstructed images. Once trained, it's a feed-forward reconstruction, so K-space goes in on one side and your reconstructed images appear on the other side. You've probably all seen this figure, it's from the Nature article, but the idea is that AUTOMAP typically gives you factors of 2 to 3 improvement in SNR over the conventional reconstruction approaches. What this can do for us at low field is really remarkable. So what I've shown here is a single slice as a function of number of averages. So if you look on the right, you can see we've done a ton of signal averaging, 800 averages, and on the bottom row we reconstruct with the Fourier transform, and on the top with AUTOMAP. If you're in the regime where there's a ton of SNR, it doesn't matter what reconstruction you do. But as you move to the left, where you become more SNR starved, you can see there's tremendous benefit to reconstructing with AUTOMAP versus the Fourier transform, both in terms of SNR and especially in terms of accuracy. And this is because the AUTOMAP transform operates between the learned sparse manifolds, which can actually recover SNR. Doing this in vivo gives us similar boosts, factors of sort of 1.5 to 2.6 depending on which slice. For instance, if you look on the right, you can see the noisiest slices gain the most from reconstruction with AUTOMAP. You also see that we remove a zipper artifact. So I've highlighted it in red. The scanner was misbehaving that day, and so there was a bit of a zipper artifact. You can see it in the Fourier transform, but not in AUTOMAP. And this is because the transform that AUTOMAP does on the raw data is a nonlinear transform. So glitches in K-space are attenuated by that transform, and unnatural image artifacts are suppressed in the reconstruction. So the question is, have we solved low field MRI? Well, we've learned a lot at 6.5 millitesla. We've learned that if you have homogeneity sufficient for SSFP and high efficiency coils, and you use fingerprinting for contrast, and you add AUTOMAP to get below the Johnson noise dominant regime, we actually do pretty good. Now, of course, once you understand the low field physics, you can think about different realizations. So if you're serious about building a scanner that could operate in this environment, you can take a page out of a 2007 DARPA proposal that I wrote with a very compact magnet that has the same homogeneity, a few hertz over a 20 centimeter DSV, and would be very suitable for portable applications. It requires less power to park it at higher field as well, and I know it's surprising to hear me talk about higher field, but the SNR goes like b to the 3/2. So I'm not talking about a lot. A factor of 3 in B0 would give you sort of a factor of 5 in SNR. That means a factor of 25 times less signal averaging, and that would be quite impressive. The fact that once you understand the low field physics means that you could think about building application-specific scanners motivated Ron Walsworth, Jonathan Rothberg, and I 6 years ago to found a company to build 64 millitesla scanners that could be used for portable neuroimaging at the bedside. Equally exciting is that other companies are getting involved in this space too. This is a 66 millitesla scanner built by Promaxo to do interventional prostate imaging. I will say that once you can do MRI at the bedside, you can do some really amazing things. This is a very recent study in comatose patients led by my collaborators Kevin Shea and Taylor Kimberly. These are comatose ventilated patients that were imaged at the bedside in the COVID ward. Since they were comatose, proper neuro exams were unavailable. You can see in both of these cases there were significant neuro findings, and they were able to determine these findings without having to transport these critically ill patients down to the radiology suite. So what's next at 6.5 millitesla? Well, there's tons of stuff to keep us busy for the next 20 years. Some things are better at low field, some things are impossible at high field, and some things are just plain old different and actually quite interesting at low field, and we'll talk about some of these. I can't talk about functional imaging without, of course, talking about Jack and Bruce's seminal work from 1991. And, of course, the bold effect relies on magnetic susceptibility differences between oxy and deoxyhemoglobin, and as such, it's the realm of high and ultra-high field MRI. So what kind of magic can I do at ultra-low field to give us bold contrast? There is no magic, there is no bold at low field. So I take a page from Thomas Witzel and Larry Wald's work on neuronal current MRI, where they use a spin lock approach at the frequency of interest, so like tens of hertz. And then the MRI signal is modulated by the presence of a stimulus field. Typically, these are kind of nanotesla fields we're looking for. The problem is that it's a very small effect, and bold can dominate these measurements, and also that SAR at 3 Tesla limits your spin lock duration and hence the sensitivity of the method. What can we do at low field? Well, there's no bold, there's no SAR to speak of, and the thing we're trying to measure, the stimulus magnitude, is independent of B0. This is work we published this year. This is Brage Svensson's work, and we call it steady state SIRS. You can see the sequence on the left. It's a spin lock sequence wrapped in an SSFP sequence, and the idea is that if there's a stimulant current at the spin lock frequency, you get an effective tip angle, and that tip angle over multiple TRs can have a big effect on the steady state signal. In fact, it's a huge effect. It's a sort of 1% effect at a 1 nanotesla level stimulus range. This is more than 100 times larger than the standard SIRS experiment. So this is a really nice new approach, and we're working on some in vivo measurements right now. So reduced susceptibility artifact can eliminate the bold confound if you want to do neuronal current imaging. It can give you more information in the presence of magnetic susceptibility artifact. And it can also enable field operation. And what do I mean by that? In this case, I literally mean doing plant root imaging in the field in clay soil in College Station, Texas. This is part of an ARPA-E project that I co-lead. We're not the first people to do plant root imaging with MRI. Paul Bottomley did this in 1986. But within a year, he recognized that natural soils, especially clay soils, have a lot of paramagnetic impurities that lead to poor image quality at 1.5 Tesla. So we built a scanner that operates at 47 millitesla, that's 2 megahertz, and we're imaging plant roots right there in the ground, and you can see them here in this animation. We published this work just this year in Geoderma. So what about contrast? If you're interested in, say, gadolinium injection at ultra-low field, you're out of luck because paramagnetic GAD has effectively no contrast at low field. But we have a new approach that we just published a few weeks ago. This is David Waddington's work using spions, superparamagnetic iron oxide nanoparticles. And spions are quite remarkable. They have 3,000 times the magnetization of gadolinium, and that magnetization persists even in the ultra-low field regime. This gives us huge relaxation and susceptibility at ultra-low field. If you look at the image on the right, an SSFP image of these things shows huge banding artifact. That's something like a 10 hertz frequency shift at Howard field strengths. So you can exploit the properties of the SSFP signal equation to make yourself more or less sensitive to off-resonance signal. These are figures from the paper. This was a rat study. If you're interested in looking at relaxation contrast, then you use a large tip angle that makes you sensitive to the on-resonance effect, and you can see pre and post, it looks just like as if we had used GAD, right? You have dark relaxation contrast. But if you're interested in susceptibility contrast, you can use a small tip angle that sensitizes you to the off-resonance effect. And in this case, we see bright susceptibility contrast where the liver lights up because that's where the spions tended to go. This is a really interesting approach because number one, it's not GAD. It also gives you bright or dark contrast depending on how you operate it. And in fact, it may be the only option at low field. I showed this figure earlier about the dispersion of T1 at low field, and this is well understood in terms of macromolecular exchange and diffusion processes, things that happen at timescales like 1 over the Larmor frequency, which for us is a couple microseconds. This has motivated people at high field to do T1 rho for stroke and other reasons. But for us, we can just use our native T1. So this is fingerprinting in a rat head. We published this in 2016 at the ISMRM, and this is an MCA occlusion experiment, and within 20 minutes in the hyperacute stage of occlusion, you can see huge changes in T1, 25% increases in T1, increasing all the way to 100% within 24 hours. So native T1 at ultra low field is a very interesting marker for hyperacute stroke, among other things. So low field MRI and hyperpolarization, they have a long history. It's really what motivated this work. But my collaborators and I have been sort of emerging a new perspective, and this is really around Simon Duckett's 2009 innovation of SABRE. What is SABRE? Well, it's a very elegant way to transfer spin order from parahydrogen into polarization into a target molecule mediated by a J-coupling, typically through an iridium catalyst. And the reason I'm bringing it up in this context is that it is maximally efficient in the Millitesla regime. It's also incredibly simple to implement. You can have huge polarizations greater than 50% and enormous flexibilities of substrates. One example, SABRE is a deep topic, but I want to just give one quick example from a paper we published earlier this year, is in hyperpolarized N15 pyridine. So what I'm showing here on the left is a proton spectrum, and on the right an N15 spectrum acquired in 100 millimolar hyperpolarized N15 pyridine at 6.5 millitesla. These high-resolution J-coupling dominated spectra are incredibly sharp, and it's fascinating because there's no dipolar splitting at this field strength, but you can still resolve J-couplings. Combine this with other work from my collaboration that we published last year showing that you can have very long, greater than 20-minute T1s in nitrogen and FDA-approved molecules like metronidazole, combined with the fact that you also get enormous chemical shifts, like 300 ppm chemical shifts, mean that SABRE plus low-field MRI could really be a new platform for molecular imaging using a wide choice of substrates in your favorite molecules. You can also flip the script on the typical way that you hyperpolarize over here and then transport over there into your scanner using Overhauser MRI at ultra-low field. This is work we showed in 2017 in nanodiamonds. Nanodiamonds are biocompatible, they're just carbon, right? But they have surface defects that are essentially electron spins. Electron spins, Bohr magnetons, are 660 times larger than nuclear magnetons, and so you can transfer that huge polarization reserve from the electrons into the proton side by driving it at the ESR frequency. That frequency for us is like 100 megahertz at 6.5 millitesla, which means you can hyperpolarize right there in the scanner. So what we've done here is take an image of a phantom that has either water or nanodiamond and water in different vials, and you cannot tell the players without a scorecard here with the regular MRI scan. But if you If you turn on the Overhauser DNP field, 191 megahertz, then the diamonds light up. This is a really interesting approach because you get RF switchable polarization right there in the scanner. You can do this in vivo. In this case, this is aqueous stable free radicals, not nanodiamonds, but the idea is exactly the same. You just need a source of electron polarization. This is work we published in 2018, and it looks just the same way as it does with nanodiamonds. You get a huge signal enhancement, and you get a big phase inversion. This is done in the heads of living rats. So I would be remiss if I didn't offer at least some advice for those of you who want to do this yourself as an experimentalist, especially since there's so much to keep you up at night, mostly obsessing about noise for. So the first thing is really to get yourself a good spectrum analyzer and learn how to use it. That will definitely help you get some good night's sleep. The second is you don't have to build everything yourself. Thankfully, there is growing industrial enthusiasm, and so you can get, for instance, gradient power amplifiers, linear gradient power amplifiers that are compatible with our operation in the hundreds of kilohertz Larmor frequencies. And speaking of hundreds of kilohertz, it used to be very challenging to get low noise preamps in our frequency regime because everyone was building preamps for so-called normal MRI. And since we do abnormal MRI, now these same companies are building preamps that actually have noise figures that are even better than what's attainable at high field. So in conclusion, hopefully I've shown you that MRI is indeed possible in the Millitesla regime through a combination of physics and compute. And I've given you a couple examples of MRI beyond the standard model, including spin lock imaging and switchable contrast and imaging roots in clay soils. And then when you add to that hyperpolarization, you can do all sorts of other things like imaging radicals and nanodiamonds, and you can use SABRE for low concentration imaging of your choice of favorite molecules. We've really embraced the impossible, I think, as Andy Webb would say. What are the implications for healthcare? Well, as I've shown, the physics is not limited to the existing scanner footprint. This footprint, of course, is built on a combination of inexpensive hardware and scalable GPU compute. We do need to understand, of course, the clinical impact of the time resolution trade-off because it is always true that images made at low field are going to be lower resolution than those made at high field. But we're encouraged by words from Steve Schiff that low-cost MRI has the potential to revolutionize medical care. As an experimentalist, I'm very thankful that over the last 20 years, I've essentially been able to paraphrase Aesop Rock and that I've been able to deconstruct and then reconstruct the MRI scanner as ways that I thought were interesting. But I really need to reach out to all of you within the sound of my voice about how would you use these tools going forward? What kind of problems would you solve using low field MRI and low field MRI plus hyperpolarization? What kinds of things can we work on together? With that, I want to acknowledge my students and postdocs, both past and present, whose work in this laboratory has framed the course of the evolution of low field MRI and hyperpolarization from my perspective. I want to acknowledge my funding sources, and I want to thank you very much for listening.